In this video we will discuss the time dilation, and here we will prove that the time is not absolute quantity in the theory of relativity. So here we will consider the two frame of references S and S dash, and this is the observer in this frame at O point and the observer in S dash frame positioned at O dash. And here we will consider that clock is in this frame of reference. So when in this the light signal will move from, or you can say the oscillate between these two mirrors M1 and M2. So for this observer O dash, this clock is at rest. So I will draw it here, these two mirrors M1 and M2, and here we will consider that the separation between these two mirrors is say L, and this signal will oscillate between these two mirrors. So when it will go from here to here, and after reflection it will complete the cycle here. So let the time taken by this signal from mirror M1 to mirror M2, and then after reflection up to this mirror M1, let the time is T0, and it moves with the velocity of light. See, so this, let the time is T0, we can write this total time T0, we write this is taken by this light signal is comes out to be 2L by C, and this time we will call it proper time, because this interval is measured in the frame of reference by the observer, and this clock is at rest with respect to this frame of reference, so we will call it proper time. Now the observer, which is also measuring that how much time will take it from mirror M1 to M2, and after that mirror M1, let this time is T, is the time period for complete time period measured by this observer, which is positioned at O in the S frame. So for this observer, this clock is moving along the positive x direction. So it is moving in the positive direction. Here he will observe that this signal will move like this, and mirror will be reached at this point, not at M2 but at M2 dash. It will meet at this point, and after reflection this signal will move in this direction and will meet mirror M1 at this position. Now the position of mirrors M1 is at this M dash. So as we know that this frame of reference is moving with velocity v in this direction, and this total time taken by this signal from here to here is T. So we will say that the time taken by mirror M1 to mirror M2 is T by 2. So this distance, because it is moving with velocity v, so we can write this distance is equal to v T by 2, and this distance, because this is light signal, So this distance we can write this is equal to c t by 2. So by using the Pythagoras theorem, and we know that the separation between two mirrors is L. So by using the Pythagoras theorem, we can write this is c square t square by 4 is equal to L square plus v square t square by 4, or we can write this t square by 4 c square minus v square, this is equal to L square. From here we can write t square by 4 is equal to L square c square minus v square, or I can rewrite it like this: L square c square, I take common, 1 minus v square by c square, and this t square we can write this 4 L square by c square into 1 minus v square by c square, or we can write this as t is equal to 2L by c and root 1 minus v square by c square. And we know that this term 2L by c is t naught. So this is, we can write as t is equal to t naught by 1 minus v square by c square. So this, we will call this expression is time dilation. Time dilation, that time is not absolute. Now if we know that if the velocity, we consider that if v approaches to c, then what will happen? In that case, we know that 1 minus v square by c square term comes out to equal to 0, and t comes out to t naught by 0, and it comes out to be infinity. So this is t is equal to, so this reflects that clock moving with the speed of light, clock moving with speed of light will appear to be completely stopped to a stationary observer. And if another case is if v is very less than c, in that case we know that 1 minus v square by c square, we can write this is approximately equal to 1 plus 1 upon 1 minus v square c square. We can write this is equal to 1 minus v square by c square minus 1 by 2, and it comes out to 1 plus v square by 2c square. So when v is very small as compared to c, in that case the term v square by c square is very small, and we can neglect it. So in that case the expression t by t naught 1 minus v square by c square, we can write this t is equal to t naught. So if the clock is moving with very very small velocity as compared to the velocity of light, in that case the time interval t naught, they will remain same for the of both observers. So this is the concept of time dilation.